Okay, so for today we're going to do a practice problem on a whole bunch of stuff with regard to derivative rules and things you need to understand about in regards to the derivative. So this I thought was a unique question because of the fact that it dealt with having a table of values, a picture of a graph, and an actual function itself. So you will notice when you take a look at this problem, there's an f of x, there's a g of x, and there's an h of x. So you have kind of like a combination of a couple different kinds of functions. So I did do a little modification of the existing AP Calc problem. So you'll notice that I added in that for part A, I want to do the equation of the tangent instead of just the slope, so we could practice with some of that linear approximation stuff. I added in a little something about finding the derivative of the inverse, just to practice that, because I feel like those are things you probably haven't seen in a little bit, and who knows if they're going to come up. Okay? So let's begin with the first one. It says, find the slope of the line tangent to the graph of f at x equals pi. So as soon as you see equation of the line tangent, immediately I want you to think L of x. L of x equals f of a plus f prime of a times x minus a. Okay, we've used that so many times throughout the year. I would hope that that's something that's kind of like ingrained in your head. Specifically in this case, it would be f of pi plus f prime of pi multiplied by x minus pi. Okay, so let's start with f of pi. The function f of x is the function cosine of 2x plus e to the sine of x. So if I'm doing f of pi, and again, remember, you probably want to be thinking of your basic sine and cosine curves for some of those, basic trig values. You don't have to go too crazy with them, but that would at least give you, a basic understanding. So this is the cosine of 2 pi plus e to the sine of pi. Okay, so if you take a look at those basic sine and cosine graphs, cosine of 2 pi would end right here at 1. E to the sine pi is going to be e to the 0 because sine of pi is 0. So therefore this comes out to be 1 plus 1 or 2. It gets a little more complicated when we want to start finding the value for f prime of pi. So let's start by finding what the function would be for f prime of x. So you're going to have to use the chain rule here. When you take the derivative of so think chain rules, derivative of the outside, keep the inside the same, multiply by the derivative of the inside. Okay, so the derivative of cosine is negative sine. Keep the inside the same, 2x, multiply by the derivative of the inside, comes out to be 2. And then when you take the derivative of e to the sine of x, think of that like being e to the u du, that kind of situation. It would stay e to the sine of x, but the derivative of sine of x would be cosine of x. And after you've done that chain rule on each part of that, now you have to go back and evaluate it at pi. So again, I want to refer you back to your basic sine and cosine curves. Those will help. So negative 2 times the sine of 2 pi plus e to the sine of pi times cosine of pi. Okay, so as I start evaluating that, sine of 2 pi actually comes out to be 0, so that makes my life a little easier. E to the sine of pi would be e to the 0 as well, because that's the middle of that curve. And then cosine of pi is the middle of the cosine curve, is actually negative 1. So when you clean all that up, that actually comes out to be negative 1. So when you go back, your actual equation of your line tangent would be f of pi, which is 2, minus 1 times x minus pi. Okay? Remember, you can leave it just like that. There's no need to go any further and simplify or rewrite things in any other way. So let's get into some more derivative rule type stuff. So if you take a look at part B, it says let k be the function defined by k of x equals the h of f of x. So a composition of functions, which once again means you're going to have to use the chain rule. It's asking us to find the value of k prime of pi. So let's start by writing a function to represent k prime of x. So again, remember, chain rule means derivative of the outside, keep the inside the same, multiply by the derivative of the inside. So derivative of the outside would become h prime, keep the inside the same, so that would stay f of x, multiply by the derivative of the inside, f prime of x, and now we'll specifically start evaluating this at pi. So h prime of f of pi times f prime of pi. Okay, so as I start to evaluate, h prime of, we just did f of pi and f prime of pi, so I'm going to refer back to the previous part. F of pi had a value of 2, f prime of pi had a value of negative 1. So this is h prime of 2 times negative 1. Okay, not that that always happens where you can reuse a previous part, but it always does help if you can do some stuff like that. So h prime of 2. So where do we have h as a function? That's the graph. So if we need any h prime values, those are going to be the slopes of our graph. We specifically want the slope of this function at 2. So let's go to when x equals 2. Okay, when you do your slope, you're going down 1 over 3. So that would be a slope of negative 1/3. And that's our h prime value in that region of the graph. If you're in a different region of the graph, it might be different. It might be something like 2 or 0. It all depends on what x value you're up to. So h prime of 2 came out to be negative 1/3. Negative 1 stays negative 1. So when you clean that up, you end up getting 1/3 for the final value. Okay, letter C. I'm going to again be using the graphs and the images above, so I'm going to have to go back and forth just a little bit. Let m be the function defined by m of x equals g of negative 2x times h of x. Find the value of m prime of 2. So this one's interesting because you have a little bit of a combination of a composition, a function within a function, and you have a product of two functions. So you're going to be doing a little bit of product rule here. Okay, so let's begin by starting with product rule. If I want to find the derivative function for m of x, product rule says do first times the derivative of the second plus the second times the derivative of the first. So first, g of negative 2x. Derivative of the second, multiplied by h prime of x, plus the second, which is h of x, times the derivative of the first, which is where we're going to be using chain rule. So as I take the chain rule on g of negative 2x, derivative of the outside, keep the inside the same, multiply by the derivative of the inside. Okay? Not too much more to clean up from there, but now I have to actually start filling in the values they give me. So I'm looking for m prime of 2. So this would be the g of negative 2 times 2 times h prime of 2 plus h of 2 times g prime of negative 2 times 2 times negative 2. Lots of 2's in here. All right, so let's clean this up a little bit. This is really asking me for the g of negative 4 times the h prime of 2, which actually we used in the previous problem, which will help, h of 2, g prime of negative 4, and then obviously negative 2 is just there as part of our calculation. Okay, so when I start going back to the graphs and the information that's provided to me, g of negative 4. Okay, so g of negative 4, go to when x equals negative 4, you can see that g comes out to be 5. So that's 5. H prime of 2, we just used in the previous problem, had come out to be negative 1/3. Remember, that was the slope of the h graph at 2. H of 2 itself is just the function value at 2. So at 2, the function value looks like it's, I wish I would have given you one that's not such a weird value. What did they call it? Negative 2/3. So I guess that actually does work. Negative 2/3. Again, I would have hoped it would be a little clearer, but you just do what you can with the graph if they don't make it as clear as you could. Okay, and then finally g prime of negative 4. So I go to negative 4. I need my g prime value this time, so negative 4. G prime has a value of negative 1. Okay, and then obviously don't forget about the negative 2 that was on the end. So the rest of this is just a matter of kind of just cleaning up and simplifying. To be honest with you, and we've talked about this before, I think you're actually fine with leaving your answer just like this. You have all the correct values filled in. Remember, we had talked about there's no need to simplify, so like why simplify if you're going to risk making a mistake? That's a perfectly acceptable answer. You could leave it just like that. You would not be able to leave it at the step before because you'd have to actually show what the values are for g of negative 4 and h prime of 2. But once you get to the point where you have all the values filled in, I would say just leave it like that. If you clean this one up a little bit, this comes out to be, I believe, negative 3 when you simplify, unless I made no, that's it. And then that's it. Your value will be negative 3. But like I said, I would say don't simplify unless somewhere it specifically says you have to simplify. Okay, so now part D, technically this wasn't in the stuff that I asked you guys to do just yet in your outline, but at this point all these things are going to just kind of blend together, so I think it's just worth going over now anyway. It says, is there a number C in the closed interval from negative 5 to negative 3 such that g prime of C equals negative 4? Okay, so if you notice that you have some function values for g of x, and you have some function values for g prime of x. So this could theoretically be an IVT or an MVT question, depending on what they're asking of you. let's think first of it as an IVT question. So if I wanted to do IVT with this, I would have to look at all the values in the G prime, section of the graph and say, does it look like -4 is in between any of those values? Unfortunately, it does not look like that, so therefore I'm not going to be able to use IVT for this. So now I'm going to have to think about, can I use MVT instead? So for MVT, I need to find where's an interval where my average rate of change comes out to be equal to -4. Is that possible? And now I'm going to obviously, again, this one's a little harder than some of the ones we've done in the past because usually they would have done something like 0. But I'm going to take a guess here that I think it's going to be something to do with going from 10 to 2 because you're going down by 8 units as you increase by 2 units. So that's probably going to work out. But just to kind of verify, do the average rate of change. Okay, so if I do average rate of change, this would be the G of -5 minus the G of -3 all over -5 minus -3. Watch your signs on that. G of -5 is 10 minus G of -3, which is 2, all over -5, really plus 3, which is -2, does work out equal to -4. So there's that average rate of change that I'm looking for. If I go back to the beginning of this problem, and I should have probably copied this down here, it specifically tells you that G is a differentiable function, which is the reason why you're allowed to use MVT. So let's go ahead and actually do that full explanation for MVT. So you'd say since G is differentiable, and feel free to use the abbreviation if you want to, and on the interval, okay, from -5 to -3, the average rate of change is -4. MVT, okay, guarantees there must be a C in this interval such that G prime of C equals -4, okay? So actually, you know what I didn't even think about at the beginning of this problem, but actually maybe it's a good thing. They tell you exactly what interval to use, okay? The reason why I was obviously showing the highlighted sections is because a lot of times it's on the interval as a whole. So maybe what you want to do is start there. Start with the endpoints of the interval they give you. See if the average rate of change matches the derivative that you're supposed to be looking for. If it doesn't, then you look for an interval inside of the region that you're working with. Obviously, again, remember that many times when you use MVT, you're trying to prove that sometimes the derivative is 0, so you look for places where the values are the same in the table, but again, it all depends on the way the information is presented to you. Okay, so then the last part of this, I just want to recap how do you do a derivative of an inverse function. So it says if G inverse, that's what the little -1 is the inverse function of G, find the value of the derivative of G inverse of x at x equals 2. So if you remember when we did questions like this was a little strange. When they tell you x equals 2, that's technically an x for the inverse function. So what this really means for you is that actually G of x equals 2. And actually, I think what we had done, instead of calling it G of x, I think we had called it something like G of a equals 2. Okay, so you know there's some function value that you would plug into G that would get you to have a y value of 2. So if I look at my table right here, I can see that when I plug in -3, that gave me a y value of 2. So this tells me a equals -3. Okay, to finish finding the derivative of the inverse, this is what happens. You take the derivative now at the a value you found. Okay, so you found the a value is -3. Find the value of G prime of -3. So if I go back to my table, G prime of -3 comes out to be 4. And then the very last thing is that you take the reciprocal. Okay, so your final answer for this is that the derivative of G inverse of x at x equals 2 would be equal to 1/4. Okay, again, I have no idea if you're going to see something like that pop up, but just in case while we were going over derivative rules, I thought I'd recap it while we were on.